In this video, to set the stage for the rest of the week's material, we'll discuss the basic algorithm of gradient descent. Let's dive right in. Basics of gradient-based optimization. In our optimization process, we're interested in finding the minimizer of a loss function f. So we try to find the input x that leads to the minimal value of f of x. And x is typically vector valued. We distinguish between a global minimum, x star, that is simply a point that has an f value lower or equal to the f values of any other point, x, and a local minimum, x plus, which only has this property locally for any x within a ball of radius r around this local optimum. So visually, you can see this as follows. So there's a global optimum here. There's no point anywhere that's better or that's better than this point. And here there's a local optimum. There are no points that are better than it within this radius r. And notice from these definitions here that actually the global minimum is also a particular type of local minimum. Now let's look for some ways of actually finding these minima. So an analytical way to find such a minimum would be to look at this following fact here, that for a local minimum, x plus, the gradient of the function there actually becomes 0. So the partial derivative with respect to all the individual dimensions, so the partial derivative with respect to x sub I is 0 at this local optimum. Sometimes I say local optimum. This is equivalent to local minimum. So visually, what does this look like? Well, if we go to any of these local optima here, the gradient here is just 0. Good. So that's nice. We know that in our local optima, all the partial derivatives have to be 0. However, for neural networks, we can't actually exploit this directly. We can't write down a solution for this minimization problem in closed form. So even though we know that this holds, we still need to resort to iterative methods in order to find points where all our gradients are 0. So let's have a look at how the iterative method of gradient descent finds local minima where all the gradients are 0. This gradient descent method is, of course, the basis for stochastic gradient descent later on. And what we'll do now first is to actually derive the intuition for its core update equation, which will also be basically the core update equation of stochastic gradient descent later on. So let's say we start at a point x. And then the first question that we ask ourselves, which is the best direction to walk in order to find a point x prime such that the f value of x prime is smaller than the value of x? Well, we can compute the gradient of our function. That is what we assume. And here we see that the slope of this gradient is actually negative. And in this case, well, we also know that we want to move to the right because, well, that's where the function values decrease. On the other hand, if the slope is positive, then we want to go to the left here in order to walk downhill. So note that going to the left means that we reduce the x value. So if the slope is positive, we want to reduce the x value. And if the slope is negative here, we want to increase the x value. So we're walking in the opposite direction of the gradient. We're following the negative gradient signal. Okay, so that's the direction we want to go in, towards a negative gradient. But how far do we want to go in that direction? Well, if we're close to the optimum, then the gradient is typically going to be small. Here, especially in, well, this quadratic function, that is the case. The closer we get to the optimum, the smaller the gradient. And we want to make a small step because we're already close. So the slope is small, we want to make a small step. And if we're far away from the optimum, at least in these quadratic functions here, then the slope is large, the gradient is large, and we also want to make a large step in order to get towards the optimum. So if the gradient is small, we want to make small steps. If the gradient is large, we want to make large steps. So this brings us to the general principle that in dimension I, we take steps that are proportional in size to the partial derivative with respect to x sub I, and we subtract that from our current value x sub I in order to walk in the direction of the negative gradient. And then there's also another parameter here that's a global parameter, alpha. So it's not an alpha sub I, but it's an alpha that applies to all the different i's. And this is called the learning rate. And this learning rate acts as a multiplier to the size of the step that we're taking in all the different directions. So this brings us to the full gradient descent algorithm, where the core part of the algorithm is precisely this update step here that we saw before. And this nabla notation here simply has the partial derivatives of each of the individual k dimensions. So this line here just writes the update equation in vectorized form for all the dimensions of the problem. And the rest of the algorithm is quite benign. We choose an initial point x here, and then while our norm of the gradient is not close to zero, so while we haven't converged, while we're not close enough to a local optimum, while our gradients are still substantial, we continue executing this update equation. And that is the entire algorithm. All right, so this brings us to the end of this video. And as always, I'd like to leave you with some questions. And I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.